Okay, yeah, I think that's a little easier to work with. Okay, so let's take a look at this. A researcher, with one of the things we start off with is we want to understand variable types. And we know the three primary ones that we're interested in when we use SPSS are nominal variables, in other words, names, numerical variables, basically anything that is on a number scale, that where the numbering is relevant and even, blood pressure, blood sugar, age, weight, height, and so on and so forth, all numerical variables. We make a little bit of a distinction there. Some of them we call discrete numerical variables. SPSS doesn't bother differentiate between them because it just handles them all as numerical variables. It happens to call them scalar, but you guys can remember that scalar and numerical really mean the same thing. On a test, or if it comes up, discrete numerical variables usually mean things that can only be expressed as an integer. So, for instance, and usually typically a small integer. So, for instance, the number of siblings that you have, right? So you might have one brother and sister, two, six, nine. If you got a gigantic family, you have 13 or something like that, right? Those would be discrete numerical variables. If you see blood pressure reported as 95 or 80 or 100, right? Well, that's kind of, they express it often as an integer, but really, when they take that measurement, they're just rounding that to 100, right? It could be, instead of 100 millimeters of mercury, it could be 100.1 or 100.2, but they'll just call it 100. So it's really hidden in there. I mean, it may look like a discrete variable, but it's really numerical. So it's really only integer variables they usually call that. But that's only really a distinction for maybe an exam or something like that. Not so much something that's going to come up in real life much. Okay, so researcher records for each participant in a clinical trial amount of alcohol they consume per month and their cholesterol levels. Indicate whether each variable is alcohol, quantitative, cholesterol, quantitative. What do you guys think? Right? What do you guys think on that? Right? Well, based on what I just said, well, the amount of alcohol is the number of drinks, for instance, but it's per month, so it's going to be a big one. And it might be half, right? It might be 3.5 per month, 4.5 per month, and so on and so forth, or 10 per month. So they're both quantitative. You could maybe call the alcohol a discrete numerical or quantitative variable, but again, it's a distinction that we really don't have to make for the most part. We're really most interested in distinguishing quantitative from categorical or numerical variables. Anybody remember what the third kind of variable that's important to us is? Also used in SPSS. It's an ordinal variable, right? An ordinal variable can be expressed as a name, or it can be expressed as a number. So, for instance, a grading scale of poor, fair, good, and excellent is it's a form of a categorical variable, but a special form called an ordinal variable because it has levels, it has order. So excellent is better than good, and good is better than poor, and so on and so forth. Now, it may not necessarily mean that the levels, that it's an even scale, that one value is twice the other, or the next one is twice that one, or anything like that. It may not have that kind of quantitative aspect. For instance, pain scale. You can have pain scale of 1 through 10, 10 the most pain, 1 the least pain, and everybody's 8 will be different, and there's no way for you to really measure that. So it's not really a numerical variable. So we call it an ordinal variable, even though 8, we all can agree 8 is greater than 6 and greater than 2, and so on and so forth. And in fact, the other problem is that there's no way to quantify whether the difference between 8 and 9 is really the same as the difference between 2 and 3, even though they're one integer apart or one value apart. Okay, so those are really the distinctions that we're really interested in. Each participant, race, ethnicity, and the severity level of depressive symptoms. Okay, so what do we have there? Race and ethnicity, right? Well, that's going to be what do you think? Categorical, right? And what about the depressive symptoms? How are they going to categorize them? Right. Well, that's going to be a tough one. because it depends on the scale that they use. But most likely, um, uh, mechanical quantitative. Well, we know that the severity is going to indicate that there's some order to it, right? So since there's some order to it, like one person has a higher level than another person, and so on and so forth, I would probably call that either quantitative or ordinal, right? Well, I don't see ordinal in there as any of the choices. So I think we're stuck with categorical and quantitative. Now, if one of these had been ordinal, then we'd have to take a closer look. What did they really record? Did they record a score on a test, which could be like 73 and a half or something like that? Or did they receive severe, less severe, moderate, and so on and so forth? Okay, so let me see that comment there. Okay. Yeah, exactly right. Likert scale. Yes. So, okay, an examination of the medical records of 10,000 women showed that those who were short and fair skinned had a higher risk of osteoporosis. What type of study was this? So we have 10,000 women who was how did they get this information? Let's see. They got this information by going to these women, probably looking back to see if they had been diagnosed with osteoporosis, right? So they surveyed 10,000 women and they asked them, have you had this diagnosis? So they're not starting with 10,000 women who do not have osteoporosis and looking towards the future, where they're surveying women and asking them if they have osteoporosis. They reviewed their medical records, in other words. Okay, so we're going to call that a retrospective observational study. Okay, maybe we go over the lab for week 3 or get the answer key soon. Oh, somebody had mentioned that to me, that on the lab I had given some extra examples and stuff like that, but I didn't put I went through the exercises. I kind of like free spooled kind of the exercises. I didn't really actually go specifically through every one of the uh, uh, exercises that I put out there. And also, when I did it orally, I didn't actually, I guess, type in the answers or anything like that. So, yeah, I'll put that up after I get done with this. Maybe I'll have to go out for a little while. Maybe about 3 o'clock or so, I'll have that posted. Okay. Okay. I think somebody has a problem hearing this. I think everybody else is okay. Make sure your speaker is turned on and you have the right output selected. Okay, in other words, that you're using a speaker on your computer or you're using headphones or something like that. It's going to the right spot. Okay, so among a group of men who were tracked for 10 years, who had scored 130 on intelligence tests, were more likely to suffer severe depression than those who had scored below 130 intelligence tests. What type of study is this? Okay, so they started with people 130 with people who they had scored on an intelligence test, some over 130, some over 130, and then they tracked them going forward for 10 years. So clearly, that's going to be a prospective study instead of a retrospective study, right? Another distinction. Which of the following is a reason to use randomization? Okay, I think some people had some issues with this particular question. Okay, if I recall correctly. Let's see. So what's our argument for using randomization? Well, we don't want our study to be biased, right? So, in other words, if we're studying how if asbestos causes lung cancer, right? Well, we know there's other factors that cause lung cancer as well, maybe genetic, maybe smoking, and so on and so forth. So we don't want to accidentally get into a situation where we wind up sampling too many smokers in one group versus another group that we're comparing it to. So randomization is an important part of putting a study together. To balance the groups on variables known to affect the response, again, smoking, for instance. To eliminate possible researcher bias, of course, that's always a problem. In other words, when you're interviewing or when you're giving someone, say you're in drug test and you're giving someone a placebo or a test drug, right? If the researcher knows which is which, in their presentation of material or as they interact with the patient, they may give that information away. So we want the placebo and the drug to be randomized, and we don't want the researcher that's applying the drug to know which one it is either, right? So that's going to be also going to be relevant to this. To balance the groups on possible confounding variables. Again, if we're comparing one exposure, we want to make sure there's as many smokers in one group as there are smokers in the other group. Great. Okay. I'm glad to hear you got the speaker issue worked out. Okay. So, Jay, it looks like all of these are like reasonable, right? So we know it's not none of them. We could check off any one of these, but in fact, probably the best answer here is all of these. Okay, let's see. Now, Cespedes is the study that I think we read in class. So let's see. What type of study is this? Study can best be characterized. I don't, off the top of my head, I don't remember it right now, but my recollection is that it was an experimental study. It compared two groups, right? So I think the answer there was experimental. If we get a chance to go back over it. Austin study can best be characterized, and I think this one was an observational study. Okay, we didn't actually have two groups that we compared or anything like that. In SPSS, variables are typically recorded. Well, let's take a look at SPSS. Let's open it up so we can answer these questions. Oh, yeah, that was the cardiovascular disease one. Okay. Okay, let me get rid of this. Okay, so let's take a look at this. So if I enter data in here, I'm just going to type data in 12, 23, maybe these are ages, 34, and so on and so forth. We'll notice that the column is automatically given a name called VAR for variable name. And over here, I'll put in a 1, a 2, a 2 again to represent 1 representing male, 2 representing female. And again, we can see that in the columns, we have our variables. In the rows, we have our cases. In other words, this is subject 1, who's 12 years old and is a male. Subject 2 is 23 years old and is female, and so on and so forth. So in our columns, variables are typically recorded in the columns, and the cases are typically recorded in the rows. The only caveat to that is that when you go into the variable view, well, now all the rows are variables, right? This represents column 1, this represents column 2, and all the details about that variable, what kind of variable it is. So for right now, this SPSS sees these as unknown variables. Well, this one we know is age, so I'm going to call it a scalar variable. This one we know is gender, so I'm going to call it a nominal or categorical variable, if you want to use that term. Since it's a categorical variable, I can define values for it. 1 represents male, and 2 represents female. Whoops. Add and say OK. Now if I go back to the data view, we can see it gave us the information on what those values 1 and 2 represented. But now we know that this is a variable and this is a variable. The other thing I could do if I wanted to is I could change the automatic variable name that it gave it to the one that we wanted to represent. Whoops. And we'll go back and we can see that that's going to be at the top of the column. Now. It's going to be a little bit clearer. Okay. Okay, so typically recorded in variables are typically recorded in rows. Okay, at SPSS, cases typically, columns and rows. Crude rates are preferred over age-adjusted rates for comparison between populations or groups or trends over time. Let's think about that. What's the difference between a crude rate and a age-adjusted rate? All right. So, how many of you guys did the exercise on age adjustment? Right? Did you guys go through that and give this a try? I know some of you guys from my online course, you kind of like that's kind of like a separate topic that we pushed in there between sessions, I think. Did you guys give that a try? I see. I saw somebody did give it a try. Okay. So what was the advantage of using age-adjusted rates? Well, if you're comparing two populations, and for instance, one population is much older than the other population, well then, if you're looking at the rate of, say, certain diseases that are more common amongst older people, cardiovascular disease, cancer, and so on and so forth, it may bias the results. So it seems like that population is more at risk for a disease rather than really having it at the same rate as the other population, but just simply having a population that's older so that the crude rate is different, but then the age adjusted rate maybe is the same or maybe even lower if, in some cases, right? So we usually prefer the age adjusted rate in order to evaluate and compare a couple of populations. Okay, let's move on to the next one. Maybe we'll even like talk a little bit about 3 if we can get to it. Okay, I can close this, I think. The page. Okay, this is 2. Questions 1 and 2 on here, on part 1? Was that 1 and 2 on part 1 we're talking about? Okay, let me just go back over that. Let's see if I can get it back here. Let's see, I think I have it on, yeah, I think it's easier for me to go back here, go in here, and go to here. Okay, for you guys that are on the online course, this is looking a little bit different than your version of it. Okay. Okay, researcher for each participant clinical trial consume the amount of alcohol they consume each month, is recording the amount of alcohol they consume each month, and their cholesterol level. Well, the amount of alcohol they consume each month is probably going to be the number of drinks, and their cholesterol level is going to be a number, right? Milligrams per deciliter or something like that of whatever kind of blood lipid that they're measuring, right? So both of those are going to be numbers. So they're going to be categorical. We talked about, maybe, numerical or scalar, as SPSS calls it. So we have a choice of basically 3 different kinds of variables: categorical or numerical, if you want to call it that, categorical or nominal, categorical and nominal, if you want to call it either one of those. Scalar or quantitative or numerical, all 3 of those basically mean the same thing. I mentioned scalar because SPSS tends to use scalar. Or ordinal. And ordinal is, again, just basically a categorical variable, but it has orders, like an order, like good, fair, poor, and so on and so forth. It's not just a name like redheaded, blonde, brunette, or something like that. So both of these are quantitative variables. So quantitative and quantitative is the only one that identifies both of these as quantitative. So we look at that. Now, what about ethnicity? Well, ethnicity is going to be a category, right? White, black, Hispanic, and so on and so forth. So race and ethnicity is going to be a categorical, also called nominal variable, and the severity of depressive symptoms. Well, that's going to be, that implies some order. Something's bigger than something else. So that's going to be either ordinal or numerical, depending on how it's measured. Now, I don't see ordinal in here anywhere. So I'm saying to myself, in that case, it's got to be numerical, right? So what do we have? We have categorical and numerical or quantitative. They call it quantitative. So we can mess with a lot of words here that mean the same thing, right? Quantitative, scalar, numerical, and so on. Okay, so let me get back to the other part. I hope that helped. Going back over that for a moment. Oops, let me go back here. Okay, so we're back at this. Okay, now this is where we got into the next week. Second week, we got into displaying data graphically, descriptive statistics. We got into the beginning of what we're going to be working with this semester. Okay, so let's take a look at this histogram. Now, interesting about histograms, let's take a look at this. Histograms represent the frequency of different values, different numerical values for each case. So, for instance, if you're 62 inches tall, say between, these are kind of markings in the middle, so I'm going to say that this is 62 in one day up to 62 2 and 355 days. And then this is 60. Well, this actually it's halves, isn't it? 60, 62, 62 and a half, 60, 60, I'm sorry, 63, 64, 65, 66. So if you're 62, you're going to be in this bar. The minute you cross over to 63, you're going to be in this bar. So these are butted up against each other because it's a continuous scale down here. It's a continuous numerical scale down here. So you're always going to be in one of these things. The only reason there's a gap here is because it happened there was no one that was 67 in this particular histogram, right? So otherwise, if there were anybody at 67, it would be continuous all the way across. The height of the histogram, the bar in the histogram, represents the frequency, the number of cases or people that are in that bar, in that age range of 62. So we have two 62-year-olds. We have 10 64-year-olds. We have 11 71-year-olds. So let's take a look at the nature of this histogram. What best describes the shape of this distribution? Okay, well, skewed to the right, yeah, I don't know. It's got a lot of people at this end, a lot of people at this end. That's kind of tough. Bimodal, well, gee, yeah, look at that.
This is height,
the mode
right?
is the most frequent value. It's kind of a hinky tool to use because the way if these bars spanned 3 years instead of one, we might not see the same shape necessarily. So it's kind of like a little bit of a hinky tool, and we could have more than one mode, right? So, for instance, in this case, we have 64 is a mode; it's a frequent value, and 71 is a mode; it's a frequent value. Now, if you use software, it might say because this is the highest number, it might call 71 the mode for this distribution. But really, there's two modes here once we see it graphically: 64 and 73, 71. So how would we describe this? Symmetric, not symmetric, skewed to the left? I'd say bimodal is probably the best answer in there. It's the height. Yeah, the height is the frequency of the particular value, 64 at 64 years of age. I'm not sure what I said, but I'm trying to talk pretty fast to get through all of this. A nurse measured the blood pressure of each person who visited a clinic. The following is relative frequency histogram for systolic blood pressure readings for those people aged 25 to 40. Blood pressure readings were given to the nearest whole number. Again, notice that they mentioned the nearest whole number. Okay, so let's see, from 100 to 110, we have, now notice it says relative frequency. That means that we're not talking about the number of people, right? But we're still talking about a frequency. But the frequency is expressed as the percentage of people out of this group of whatever it is. Let's for the moment argue that, let's for a moment to make things simple, say it was 100 people. So 15% of those 100 people had a systolic blood pressure between 100 and 110. So that would be 15 people out of 100. Okay, but in this histogram, it's expressed as a proportion or a percentage. 35% of the people had a blood pressure between 110 and 120, 25% between 120 and 130, and so on and so forth. And the least frequent group was 150 to 160, right? Well, only about, looks like, I'm going to guess here, about 3% of the people are represented there. Now, if this is all of the people, in other words, there weren't any outliers that they didn't show here on this distribution, then if we added these all up, 15, 35, 25, and so on and so forth, it would add up to 100%. Got another comment there? How would you figure out the median from that histogram? I would call it bimodal and say that it had two modes, the lower number and the higher number. Software might call it just the higher number. In other words, if you went and put that data into Excel or SPSS, it might just give you a single number, and that would be the most frequent outcome, which would be 71. Which I think was 71. By the way, think about this for a second. Let's say that you have 100 people and you measure their age, right? Let's see. Not so much. I'm trying to think of something that might have a decimal attached to it, or a big number. Let's say their blood sugar. Now, their blood sugar be anything from 0 to 600, let's say, right? So let's say you measured it and it was in 3-digit numbers to 3 digits, and it was like 25, 75, 95, 103, 102, 104, and so on and so forth. You can imagine that if you made a histogram of that, that the range, that if you look for a mode, well, the mode might only be 3 people out of 100 that all had exactly the same number, like 103 or something like that, right? So the mode's kind of a sloppy measure in terms of the other ones that we use. We use mean and median much more extensively than we use mode from a practical perspective. But it's good to understand if you have a distribution that's not normal, that is multimodal. So that's really what we're looking for there. Approximately what percentage of the people aged 25 to 40 had a systolic blood pressure of at least 110, but less than 120? So 110 to 120. So what percentage does that represent between these two numbers? It means that's that one bar, which is 35%, right? Pretty clear? Okay, 0.35 or 0.35%. Don't get fooled by this, right? 0.35% is less than 1%. So it's really 35% or 0.35. A nurse measured the blood pressure of each person who visited her clinic, following a relative frequency histogram for systolic blood pressure readings for those people aged 20. Same one, same chart. Approximately what percentage of people aged 25 have systolic blood pressure less than 120? Well, less than 120 would include both of these bars in the histogram. In other words, 35% and 15%. So half of the people, 50% of the people, would have a blood pressure between those two values. Nurse measured the blood pressure of each person who visited her clinic. Following is the relative frequency histogram for the systolic blood pressure readings for those people 25 to 40. The blood pressure readings were given to the nearest whole number. Again, same graph. Given 200 people were aged 50, 25 to 40, approximately how many had a systolic blood pressure less than 130? Okay, so now we have to, Professor Weicker chose 200 people, right? Remember I mentioned, let's assume that's 100 people for a moment, right? So what percentage of the people had a blood pressure less than 130? Well, let's see, it's going to be 15% of the people, 35% of the people are between 100 and 110, 35% of the people are between 110 and 120, 25% are between 120 and 130. So 15, 50, 75% of the people have a blood pressure less than 130. So if this was 100 people, it would be 75 people. 75% of 100 is 75 people. But since it's 200, 75% would be 150 people. Okay, everybody comfortable with that, right? Okay, if it would have been 1,000 people, it would have been if it would have been 1,000 people, it would have been 750. 120 would be, yeah. Well, that's actually, tell you the truth, that's a little hard to judge, isn't it? Right? Because we don't know if the 35% of the people that are in here, maybe all of them were to the lower end. Maybe the highest value in here is 150. So 115. So maybe 115. The 50th person is 115, and the 51st person is 121. We can't really tell for sure, right? We know that the median is somewhere near 120, but from the histogram, we can just get a general idea where it is. That makes sense, Holly? Okay. Okay, next one. Let's see. Proportion of adults aged 15 to 49 who are living with AIDS is 0.5%, 1% in the Caribbean, 0.9% in Central Asia, 0.6%. Suppose we include the proportion for sub-Saharan Africa, 5%, to this data and calculate the standard deviation. How would you expect this? Would you expect it to be significantly larger, smaller, or remain the same as the standard deviation without the observations for sub-Saharan Africa? Okay, anybody want to hazard a guess on that? Okay, larger. Makes sense, right? Because what is the standard deviation? Without going into the math, the standard deviation is a measure of spread, right? So if we're looking at only populations where it's 0.5%, 1%, 0.9%, 0.6%. We're looking at the spread there. It's relatively narrow. It's only from 0.5 to 0.9, right? It's relatively narrow spread. But if we include sub-Saharan Africa, 5%, well, now look how much wider that makes that spread, right? So sub-Saharan Africa basically skews this data to the right, doesn't it? Because it's an extreme value. And it makes the standard deviation, which is a measure of spread, without going into the math, which is a measure of spread, larger, significantly larger. Okay, a distribution that has the right tail longer than the left tail is considered. Okay, what about a guess on that? Okay, it's going to be skewed, right? It's going to be right skewed. And why is that? It's going to be right skewed because since the tail is longer to the right, it means we have extreme values in the right. So if we were say income, it means that we have people on the right that made very large amounts of money compared to everyone else. Now, let's say that's skewed to the right represents people making billions of dollars in the stock market one year, or somehow, or in some .com or something like that, right? Well, how is that going to affect the median for that distribution? It's not going to affect the median very much because it's only one person making much more, or a few people making much more. So the median can only go up maybe a few people, right? But the average can be dramatically affected. So instead of having a symmetrical distribution where the mean and the median are the same number, the median stays pretty much still, but the mean is pulled over to the right, right? So that tail pulls the mean to the right or positively. So that would be a positively or right skewed distribution, skewed to the right, would be right there. Okay, so there's a few ways that you can look at it that way. You can see it pulling the mean away from the mean away from the median, or you can see it as the extreme values pulling the distribution to the right or to the left. A recent survey polled a sample of male Mexican American adolescents and determined an association between smoking and unhealthy behaviors. Okay, and here it is in a crosstabs table, in a 2x2 crosstabs table. And let's see, we have the exposure, smokers and non-smokers, and we want to see if it's more or less likely that smokers among this population are more or less likely to do risky things. That's interesting. Professor Weichel laid this out kind of the way that I would, right? The exposure in the rows and the outcome in the columns, okay? Disease or the outcome in the columns. So, or the result. In other words, the independent variable and the dependent variable, the response variable. Okay, you can look at it that way also. Okay, so let's take a look at this. What proportion of sampled smokers likes risky things? Okay, so let's see. What proportion of sampled smokers? How many smokers are there anyway? There's 45 and 36. There are 81 smokers, right? So we have 81 smokers, and we have, of those 81 smokers, 45 of them like to do risky things. So I'm going to pull up my calculator. So 45 divided by 81. Check my math, you guys, in case I'm wrong. So 0.556 or 0.56, right? I'd say 2 decimal places is enough here, right? 0.56 is, or 56% of smokers like to do risky things. Well, how about non-smokers? By the way, that's also called, and we'll deal with this later on, that's also called the relative risk or risk ratio, right? I'm sure, excuse me, risk ratio we'll get to in a second. That's called basically the risk, right? So the risk is 56%. In other words, if you're a smoker, your risk of being someone who likes to do risky things is 56%. I hate the fact that that risk is in there too. It's confusing the way I'm using the term, but I'll try and stay away from that at this time. What proportion of sampled non-smokers like to do risky things? Well, this time we have a lot more people in the non-smoker group. So we have, let's see, 299 people, right? 199 people in the non-smoker group. 46% of them like to do risky things. So 46 divided by 199 is equal to 23% of that group like to do risky things. Okay, so we are asked to provide your answer as a decimal. She shows it as 4 decimals. If you really, I guess if you were literal, you could put it in as 4 decimals, 0.2312, I guess, right? Rounding at that point. I think probably 23% probably would have given you the right answer there. Okay, so I'm pretty sure it would have. Okay, so you want to know something interesting now. I don't remember what the number here was. I think it was 55% or something like that. If you look at 55% and put that over our, say, 23% on the bottom, you get a ratio of 2.4, right? But you know, what does that mean? That means that if you're a smoker, you're 2.4 times as likely to do risky things, than if you're a non-smoker. We call that the relative risk or the risk ratio. Later on in the semester, we're going to be learning more about that and something called the odds ratio and so on and so forth. So it's a little bit of a preview there. Okay. Using the North Carolina 800 data set, answer the following questions. Okay, so let's see. Average mother's age in the sample, percentage of mothers in the sample that were married, and what was the most common racial ethnic group that was in the sample. Okay, so let's go over there and get it. First thing I want to do is find it. NC birth mod. Okay. Now I want the SAV, the version of it that's here we go. Here's one of them. I wonder if it'll cooperate and open an SPSS form. Yeah, looks like it's going to work. I didn't realize I closed it. Okay, don't worry about this. If it asks you about whether SPSS changed the way it stored data, you can just simply say yes to this, that it's okay to update it, use the current version of the encoding for the data. Okay, so what did it ask us? What did it ask us to do? I'm going to get rid of the output window. We're not going to need that for, whoops. Uh-oh, I think I closed the wrong one. Oops. Yep, I closed the wrong one. Let me go back in here. You know, when they changed the operating system here, when they changed the operating system or upgraded the operating system on the Mac, they went to these dark bars, and I hate them, and they're hard to distinguish. Okay, so what were we asked here? Let me go back to that question. Okay, what is the average mother's age? Okay, let's do that first. We want the average mother's age. So we want a descriptive statistic about the mother. So where is the mother's age here? Let's see, weeks, that's the gestation period. M-age, that looks like the mother's age. I'm going to go to the variable view just to make sure. And if I look in the variable view, here is that variable described. M-age is a numerical variable. And what does it represent? Oops. I don't want to do that while we're... There we go. Okay, the mother's age represents the age of the mother in years. That's the variable that I want then. Okay, so I'm going to go back here. And in order to find the average is just the arithmetic mean, right? So let's see. I'm going to go up to Analyze. I'm going to ask it to calculate descriptive statistics for me. Frequencies typically is used for categorical variables, right? How often does this name, this color, this group occur, right? This ethnicity occur. So I'm not really interested in the frequency. I'm more interested in descriptive statistics. So I'm going to click on descriptive statistics. And I'm going to say, well, it wants to know what variable I want to work with. I want to work with this numerical variable. Notice that little scale there. Numerical variable, age of the mother. And what would I like to calculate? Well, I would like to calculate my options. I would like to calculate my mean. It didn't ask me for any of these others, right? So I could turn these off if I wanted to, or I could leave them on, right? I could calculate all those. I'll click continue, and I'll say okay. The output window will come up now and give us the answer to the analysis that we wanted to do. So it tells us the age of the mother in years at 800 subjects here, as we suspected. The range of ages is 27 years. From the youngest is 15, the oldest is 42, and the average age, the mean age, is 26.92. So that's going to be our answer, 26.92. Notice that your only opportunity here when you use descriptive statistics, descriptives, your only opportunity is to work with and calculate for the entire group at once, right? So for instance, the age, this is the average age for the mother, the average weight gain during pregnancy, the average for all 800 women. So it didn't give me the opportunity to say, what's the average age of mothers who smoked? Or what's the average age of mothers who had premature babies? Is it different than the average age of mothers who didn't have premature babies? It doesn't give me the opportunity, that selection, in order to break that up into more than one group so I can compare groups. However, we're going to see as we move forward that Explore, the next selection, does the same calculations, but it allows you to do that kind of thing. Actually gives you a bit more information too. Okay, so let's take a look at the next thing they asked for. Next thing they asked for was, let's see, what percentage of mothers in the sample were married? Well, married or not married, marital status, that's a categorical variable, right? Married or not married. Let's take a look at that in the variable view. So look at that in the variable view, marital status. I can see, well, it's a nominal variable. I'm going to click in this values. Well, there's only two entries here, married or not married, right? So we can find a percentage for that, I would think, right? So let's do that now. I'm going to go back to you don't have to go back to the data view. You can do the analysis from here if you want, but I just feel comfortable doing that. Analyze, descriptive statistics, except this time we're dealing with a categorical variable, nominal variable, so I'm going to go into frequencies. It asks us which variable you want to work with, and I'm going to say marital status. I'm going to move it in there, okay, and now it's going to give me the opportunity to ask for statistics like mean and so on and so forth. That really doesn't mean anything with a categorical variable, so by default, none of those are checked, and in fact, we're not going to bother to check any. Now, if I want, I can produce a chart from here also. For instance, I can produce a pie chart, and I can have that pie chart describe the groups, married or not married, by frequencies, the number of women, right, that were married or not married, or by the percentage of women that were married. I'll put percentage for this particular analysis. Then I'm going to click OK. And we're after that percentage, right? So here we go. The percentage of there were 537 women in this group that were married. That's 67.1% of the population of the sample. The not married group was 32.9%. And here it is displayed graphically as well. So the percentage of women that were married is 67.1%. Okay, is that what they asked for? Yeah, it was. Okay, what is the most common race and ethnicity? Again, race and ethnicity is a categorical variable. So I'm going to go up here and I'm going to say analyze, descriptive statistics frequencies again, except this time I'm going to move marital status out of our workbox and I'm going to put in, I think there's a different variable here for ethnicity, isn't it? Ethnicity, I'm going to start with race. Okay, I'm going to hope that I got the right one. I'm going to click OK. And let's see. Here is a graphic by percentage. You can remember we didn't turn that off, so it made it automatically for us. And the which is what they asked for, what's the most common race or ethnicity? And in this case, it was white mothers, who represented 75.5% of the mothers that were in this survey. Black mothers were 21.1, American Indian was 1.5%. These are the actual frequencies for these different mothers. If they were missing, that's a good question. If they're missing values, which of these should you use as the percentage? I think by default, I believe that SPSS does not count the missing values. It eliminates them. It's as if they weren't part of the survey. So, I mean, you could argue that you should use all the women in the survey, but then it doesn't seem like that would be right either because you don't know what their ethnicity was, right? So CHS, what's CHS? Did I say CHS? Is that a different variable here? I'm losing the reference there to CHS. Oh, it's the database for the project. Oh, okay. There you go. Okay. That's with and without. And in fact, I wonder if see on this one we don't know. There's no missing values. I tell you what. Let's do a little experiment here. Okay. I'm going to go to the data view. I am going to go down here, and I'm going to add a person. Whatever that is, one. Whatever that is, one. Okay. And I'm going to go to ethnicity, and I'm not going to put anything in. Now I'm going to do the analysis again. Descriptive statistics frequencies, and I'm going to run it again, see what it does with it. Okay, this time there should be one missing value here, missing one. Okay, and how does that compare to here? Let's see. So we have, I would really need more to be able to see, right? So the total is 99.9. It looks like it valid percent 1.5. Yeah, you're right. It did it both ways, right? It did it both ways. It did it once. You can see that if you ignored the missing value, it was 75.5% white. If you included the missing value, it was 75.4% white. So it actually gives you the both versions of it. Actually, we should have seen that right here. Like we saw both columns were available. Cool. Okay. So SPSS. So we solved that problem, that issue on our own. Okay. Good. I feel good about that. Okay. So let's see. This next question is. What was the median mother's age? What median mother's age for mothers who smoked during pregnancy versus mothers who did not smoke during pregnancy? Well, now we have a problem, don't we? I'm going to go up here to analyze descriptive statistics. I'm going to go into descriptives first, and I'm going to ask for the average age again. Okay, I must have remembered that from the last time we did this. Here's the average age, right? I mean, previous semester, because I used the same example as we were talking. The average age 26.92, but it doesn't distinguish between mothers who smoke and mothers who don't smoke. And in fact, analyze descriptive statistics descriptives doesn't give us the opportunity to tell it to distinguish between them. However, if I go to analyze descriptive statistics, explore, right? Well, now my dependence list, that's the variable that I'm finding the descriptive statistics for, the age of the mother. Now I want to break that up into two groups, mothers who smoked and mothers who didn't smoke. So I'm going to go over here and let's see, smoked during pregnancy. That's a nominal variable category, right? I'm going to move that into my factor list. So basically I'm factoring or breaking up, look at factors, breaking up the data for the age into two groups. Women who did smoke, I'm going to do one analysis. Women who didn't smoke, I'm going to make believe it's two different samples, right? And then that'll allow me to compare them. I can go into statistics here, and it's going to find all the descriptives. I don't have to worry about 95% now. That'll come later. And I'm going to say, okay. So when it completes this analysis, now notice it gave us a summary of the data, if there was any missing values, and so on and so forth. But it also gave us a rundown of many statistics for both groups, right? So for the group that had 684 women, mothers who didn't smoke during pregnancy, the average age was 27.11. The median age was 27 years old. And for mothers who did smoke, the average age was 25.7, and the median age was 24.5. Okay, the reason why I mentioned both of them because I've already forgotten which one of the two they asked for. They asked for the median age, right? So it was the median ages that you would put in there, and she asked for it to 2 decimal places. Okay, so I think the last question is, were there any outliers in the mother's age in either of the smoking groups, smoker versus non-smoker, inspect side-by-side box plot? Well, you want to know, there's a dirty little secret there I didn't point out to you, right? And that is, whenever you do analyze descriptive statistics and explore, whenever you do that in that, whoops, cancel, I got the wrong one here, wrong data set. Did I close it? I must have closed it. Open, recent. There it is. Yes. Must have been inadvertently closed it. Okay. Whenever you use analyze, descriptive statistics, and explore, one side benefit you get, okay, I'm going to put age of the mother, smoking status, smoke during pregnancy, okay. One side benefit you get of that is it's going to automatically produce a box plot for us, side-by-side box plots. But it may not necessarily produce a histogram. So I'm going to go into this plots box, and I'm going to click off histogram. Now you could also do this by saying graphs, legacy dialogues, and asking it to produce a box plot or to produce a histogram. You could do it either way. Okay, but I'm going to do it right here since it's convenient. I'm going to click OK. So now we're trying to see if these two groups, if they're skewed. Okay, so let's take a look at this. One clue is, what's the mean? 27.11. What's the median? The median is, where is it here? 27. They're pretty close. The mean and the median pretty close to each other. Okay, what about for the mothers who did smoke? Or did not smoke? 25 did not, but did smoke rather. 25.7, and the median was 20. Oh, that's a bit different, isn't it? More different than the others. Okay, let's take a look at the histograms. Well, the histograms for mothers who did not smoke during pregnancy, that looks fairly normal, doesn't it? How about the mothers who did smoke during pregnancy? Hey, well, look at this. The right tail here seems to have older mothers who were smokers here. There's more older mothers that were smokers here. It doesn't look quite symmetrical, does it? Looks like we have a lot more values to the right there. So it looks like this is skewed to the right. Well, we saw that, didn't we? We saw that among mothers who smoked, that the mean was lower than the mean was 25.2, and the median was 24.5. So the mean was being pulled to the right, or higher number, right? We can see it would look quite a bit different as opposed to mothers who did smoke. So it does look like this is skewed to the right. Let's look at the box plots that were produced for us as well. If you look at the box plots, the median, looks pretty much like it's in the center. Look how nice and symmetrical this looks. But the median for the mothers who did not smoke is the median is closer to the lower numbers than it is to the higher ages. Right? So it looks like this is being pulled to the right. It's positively skewed towards the higher numbers. So to answer that question, I'd say were there any outliers in the mother's age in either smoking groups? Well, the answer to that is no. There were no outliers. Right? I answered the wrong question, didn't I? Right? But maybe this is a learning exercise, right? There were no outliers there, were there? Right? If I go back to the output window, right? If there were outliers, values that were so far away from the 75th percentile or the 25th percentile that SPSS decided that you might want to examine them, we would see them as stars or circles above the top leaf or the bottom leaf, bottom feather or upper feather or lower feather, as they're called. Right? So we would see them, but we don't see any outliers here, at least not by the rules that SPSS uses to determine the outlier. Right? There were no outliers. However, you could argue that this group, where is it? Where did I put it? You could argue that mothers who did smoke, the distribution was skewed to the right or positively. Right? Even though there were no outliers, there were a lot of women that were A lot of older women that were smokers in that particular group. So this is certainly skewed more than the other group is. Okay, so those are the first two groups. So you guys have assignment 3 to work on, quiz number 3 to work on, to practice on, and so on and so forth. And I'll go over that. I'll go over that so we get all the answers and stuff like that. We review the answer sheet for that on maybe this coming Thursday. Okay, so I hope this helped out a little bit. It was a bit of a review because it really covered the first couple of weeks of this semester. But maybe as we go forward, we'll get more of these. It's recorded, I think, successfully. So I'll post this by early evening, and I'll also within like a few hours after afternoon, like 3 or 4 o'clock or something like that. I'll try and get those answers to the exercises that I did verbally or I completed verbally without putting in the numbers or that I didn't get to that were extra. A lot of times for the labs, I'll put in extra material so that I don't wind up with nothing to say during the lab, which is a problem. In the radio business, uh, uh, if you listen to the radio for a while or even TV, you'll notice that if they stop talking for even 5 seconds, or on TV, if something doesn't happen on the screen for 5 seconds, your brain gets scrambled. It's automatic. What's wrong? What happened? Right? Because you're used to continuous feedback from either a radio or a TV. They call that in the radio, they call that dead air. Dead air is considered the worst possible thing on the radio. So that's why you hear so many political commentators and sportscasters that are saying dumb things on TV and on the radio because they got to keep talking. They can't ever. If you notice, they talk constantly, and when you got a guy that's talking for 2 or 3 hours or something like that, he's going to say some pretty dumb stuff in there at some point. Like, let's see, I've been at this for about an hour, and I'm sure I said a few dumb things here. So take care, guys. Have a good afternoon. Enjoy the rest of your weekend, and I'll see you guys either online or in class this week.